As far as today's class is concerned, today we'll be talking about a very important case of the rods actually loaded members, what we call as the statically indeterminate loaded members, or statically indeterminate actually loaded members, or statically indeterminate members. What do we mean by the statically indeterminate members? Let me give you an example. Let's suppose we have a structural member, and this structural member happens to be in the form of a rod. Let's suppose we are having a prismatic rod. When we say a prismatic rod is the one, or we often say prismatic element. Prismatic elements or the prismatic rod is the one in which two things are constant. First of all, area of cross section is constant, area is constant, as well as the Young's modulus of elasticity is also constant. Okay, this is one way of calling a rod as a prismatic rod. A rod in which area is constant, or the rod in which as well as the rod in which the Young's modulus of elasticity is constant. But you know that we also take the product of the two, that is EA, the product of Young's modulus and area of cross section. If in any member the Young's modulus of elasticity and the area of cross section is constant, we also call that member as a prismatic member. That member is also called as a prismatic member. Okay, let's suppose we have a prismatic member. We essentially take a rod. Okay, let's suppose this rod is fixed at one end and is subjected to a load at another end, such that the length of this rod is L. Okay, at end A the rod is fixed, and at its free end it is subjected to force or load, let's suppose P. Okay, then we know while we calculate the stresses and strains in this rod, we often say that the stress in the rod is equal to P by A, and we also say that the strain in the rod is equal change in length divided by the original length. Okay, now if we are asked how much is the stress at this end, okay, what we do, we will free it up. Let's suppose that this uh, let this fixed end is not here. You remove the fixed end. As we remove this fixed end, as we went on to remove this fixed end, so we have a rod like this. At the lower end it is subject to load P. At the other end it is free. Let's suppose it is subject to a reaction force. Here a reaction is generated. Let's call that as reaction as F prime. When we draw, or when we write the equations of equilibrium, we will write F dash minus P is equal to 0. From equilibrium point of view, we are writing minus P because we are treating this to be our positive y-axis, and this we are treating to be our negative y-axis. Okay, so F prime comes out equal to P. So it means if we are asked to calculate how much is the stress at this very end, at the fixed end, the stress at the fixed end will also be equal F dash divided by A. That's fine. Now if we have a case, and another case, if we take, let's suppose we are having a prismatic rod, and this prismatic rod is fixed at both the ends. It's fixed at one end as well as it's fixed at the lower end. So we take a prismatic rod, fixed at both ends. It's fixed at the lower end, it's fixed at the top end, such that the length of this rod is, say for example, L. Okay, let's call this as end A, we call this as end B. Let's take a point, let's call this as point C, and say at point C it is subjected to load, it is subjected to load P. Okay, it is subjected to load P. Now we are asked, the question states calculate calculate the magnitude of calculate the magnitude of reactions. Calculate the magnitude of reactions at ends A and B. That is, we have to say How much is the reaction at end A? How much is the reaction at end B? The question is, first of all, why there will be the reaction? The reaction will be because our rod of length L is fixed at the two ends, end A and end B, and the load is being applied at point C. This point C will try to move the material of the rod at end A in the downward direction. Okay, but the material which is fixed out here will offer a reaction in the upward direction. Okay, in the same way, the load at point C will try to compress the material at end B, and in response, the end B will offer reaction in the upward direction. So certainly there will be reactions. There will be reaction at end A, there will be reaction at end B. We have to calculate it. Let's suppose we are also given that the distance from A to C is, let's call this as L, the distance from A to C, and we'll also given this distance as the distance from C to B as L, the distance from C to B, such that LAC plus LCB is equal to the total distance L. This is quite given to us. Now the question is, we have to calculate the reaction at end A and the reaction at end B. In order to do this question, see how complicated this question becomes. Let me rewrite this question or redraw the diagram of this question. The question is like, so we have the rod which was fixed at two ends. Let me remove the two ends. Okay, so at point C it is subject to the load P in the downward direction. Okay, and I stated that at end A there will be a reaction in the upward direction. Let me call that as reaction at end A, and at end B there will be the reaction in the upward direction. Again, let me call that as reaction at end B. This is RB, this is RA. The question is why there will be reaction here at end A, because I stated that the load P is trying to move the material in the downward direction. It offers the reaction in the upward direction at end A. Similarly at end B, it tries to move the material in the downward direction. The material will offer the reaction in the upward direction. This distance is also given to us. This is LAC, and this distance is for us LCB. Okay, that's fine. Now we write the equations of equilibrium because we have to find the magnitude of RA and RB. Okay, all the distance, all the forces that we measure in the upward direction, will be taking them as positive. All the forces we measure in downward direction, will be taking them as negative. Okay, so it means as we write the equation, writing the equation of equilibrium, writing the equation of equilibrium, as we write the equation of equilibrium, we write RA plus RB minus P is equal to 0. That is RA plus RB is equal to P. This is our equation of equilibrium, and let's call this as equation number 1. Now the problem is we have to find the value of RA and RB. So we are having two unknowns. We are having two unknowns. Our unknowns are RA and RB. But we are having only one equation, that is RA plus RB is equal to P. And we know from mathematics point of view, if we have two unknowns, in order to solve an equation having two unknowns, we require two equations. But here we are having a single equation and two unknowns. Okay, so this problem becomes for us what's known as statically indeterminate problem. This is a statically indeterminate problem. This is a statically indeterminate problem. Why this is a what do you mean by statically indeterminate problem? When number of unknowns, when number of unknowns in a problem, when number of unknowns in a problem are greater than the number of equations, such a problem is known as the statically indeterminate problem. That's what we have in hand. We're having a problem in hand where the number of unknowns are more than the number of equations. This becomes a statically indeterminate problem. In order to solve this type of a problem, in order to solve this type of a problem which has a statically indeterminate problem, what we do, we have to we look for some other equations. Okay, because we, at the end of the day, what we have to enhance our equations. Okay, Enhancing our equations means that the real problem is that we are having two unknowns, Ra and Rb, and we are having only one equation which we have to solve. In order to do this, what we require an additional equation which we can use with this Ra plus Rb so that we get the value of Ra and Rb. Okay, and the equation that we are searching for is known as, is called the compatibility equation. Okay, we search for an equation that's called the compatibility equation. And what do you mean by compatibility equation? You look at the physics of your problem. The physics of the problem is very simple, that we have a rod which is fixed at two ends. This is fixed. Fixed means it does not allow the motion. There is no rigid body motion in it. Okay. So we are having a rod which is fixed at both ends. It's fixed at end A. It's fixed at end B. Okay. Length of this rod is L. This is the physics of the problem we have, and it's subjected to load at P. Okay, load P at point C. Okay, and this distance is LAC, and this distance is LCB. That's it. Okay, look at the overall physics of the problem. The rod is fixed at end A, it's fixed at end B. So there is no motion from end A to end B. Okay, end A will not allow the material to go down, end B will not allow the material to go up. So it means the total length of the rod does not change. Total length will not change. The total length will never change in this case. Had the rod been free from one of the ends, had it been free at end A or at end B, then the length will change. But it's fixed at both ends, the length will not change. Length will not change. It means that the change in length in the material will be equal to 0. Okay. So this gives us this change in length is equal to 0 gives us an insight of solving this problem. Okay, so I can rewrite the entire problem as, so what we have, I have two equations. I have reaction at end A, I have written that as Ra. Okay, so it's like Ra plus Rb is equal to P. That's my equation number 1. Okay, and the second equation that I have just realized from the physics of the problem is the change in length is equal 0. Okay, this is my equation 2. Okay, I will make use of this equation 2 to solve equation number 1. Now the question is how. Look into your problem, return back to our problem. Okay, as we return to our problem, we have taken this rod Okay, this is my end A. So here we are having reaction Ra. Here we are having reaction, let's call that as Rb. At end C, we're applying a load, that's called load B. Fine. This distance we are writing as LAC, and this distance we have written as LCB. Okay. Now the total change in length is equal to 0. Okay. So what we will do, let's do an otherwise process. Let's take a section out here. Let's draw a section first here. Okay, and isolate the section. As we isolate the section, so we take a section like this. One end of the section has a reaction load Ra. Okay, one end of the section has, but this portion is in equilibrium. This portion will be in equilibrium only when in the opposite direction we'll be having a force acting that should also be equal to Ra, because we have taken a section out here. This is our sectional line. The portion of the material above the sectional line is in equilibrium, and the force acting on the section is Ra. Since this portion is at equilibrium, it only indicates that there has to be the force acting in the downward direction. Therefore, this will happen in the entire, even if we draw a section over here, if we take a section over here, okay, at a distance LEC from end A, even then, when we draw the free body diagram, we'll be having only these two loads, Ra and Ra, acting on the machine element, and the length of this element will be equal to LAC. Under the influence of this Ra, which is a tensile load, how much will be the change in length? I will write the change in length, okay, because change in length in the end AC will be equal Okay, I have already the formula delta L is equal to PL divided by AE. Okay, this is the formula for the load P. Now for load is RA, therefore the change in length will be equal RA length of the element, that is LAC, divided by area of cross section multiplied by the Young's modulus of elasticity. Let's call this as equation 3. And if you look at the element, this RA, you just try to see this RA. This RA is tensile, that's why this delta L is positive. Now take a section. Where will we taking the section? Let's take a section over here. Let's take a section. Okay, let's again talk about the section. Let's take a section again here now and isolate this portion. Okay, and assume as if the external load P is not acting. Okay, as if the P is not acting. Isolate this out. Fine. Isolate this RB out. Therefore, if you as we isolate this portion RB, so on this element, the load acting is RB in this direction. This length is LCB. Fine. This portion will be in equilibrium when we will be having a load acting in this direction such that that is also equal to RCB. We don't have to take the external load P into consideration right now. Why? I will discuss that later on. Therefore, under the influence of RCB, what will be the change in length for the element CB? The change in length for the element CB will be delta L for the element CB will be equal load on it. Let me call that as load is RB, length that is LCB divided by area into Young's modulus of elasticity. If you look at the load is compressive. That's why I will write this as minus and write this as equation number 4. So delta LAC is the change in length of the element AC. Delta LCB is the change in length of the element CB. But you know how much is the total change in length? The total change in length is 0. Okay. So we can therefore write this as the total change in length is 0. Okay. So we can write it as since the total change in length delta L is equal to 0 and our delta L is delta LAC plus change in length in the section CB is equal to 0. There is no change in length. That means applying equation 3rd and 4th, I could write RA LAC divided by AE and we have minus RB LCB divided by AE is equal to 0. Okay. So therefore we can write it as can be written as RA LAC divided by AE is equal to RB LCB divided by AE. AE goes. Therefore, RA is equal to RB multiplied by LCB divided by LAC. Okay, I will call this as equation 5. If we substitute equation 5 back into equation 1, what we can obtain? So as we write these equations from equation 1, from equations 1 and 5, what we will obtain? RA in place of RB, I will write RB plus RB multiplied by LCB divided by LAC. Okay, plus RB is equal to P. Fine. So I will take this RB out. This is RB. Internal will be LCB plus LAC plus divided by LAC is equal to P. LCB plus LAC is equal to L. Therefore, RB becomes equal P by L multiplied by LAC. Okay, this is what we had to obtain. We have to find the value of RB. Similarly, okay, substituting the value of RB back into equation 1, we'll get RA is equal P by L into LCB. This will be the value of RA. This is how we have to find. We have to find RA, we had to find RB. But the equation that we had only one equation, and we had to get the value of two unknowns, RB and RA. So we calculated RB and RA with the help of one more equation. This is called the compatibility equation. And the overall problem was the statically indeterminate problem. Okay. In the same way, about statically indeterminate problem, we also have a case of, if I talk about uh, we have a case of what we call as the thermal stresses. Thermal stresses. Let's suppose we are having a machine element, and this machine element is again in the form of a bar or a rod, prismatic rod or a prismatic bar. And say, for example, this prismatic bar is fixed at its two ends, at end A and end B, and the length of this prismatic bar is, say, for example, L. Now let's suppose this prismatic bar is not subject to any external load except for a temperature change. Okay, let's suppose that there is a temperature change delta T to which this rod is subjected to. There is no external load. There is just the temperature difference to which this machine element is subjected. Now the question is, what will be the response of this rod to the temperature difference? What will be the response of this rod to the temperature difference? That's the question. The fact is, we know that the materials tend to expand when they are subjected to temperature change, positive temperature change. When the temperature increases, the machine element begins to expand. Okay, so same is the problem here. As we see this machine element which is being loaded, if you subject it to a positive temperature change, the material will try to expand. So as the material will try to expand, okay, it will tend to move in this direction as well as in this direction. Okay, it will try to increase in length. So the end B will offer a reaction in this direction, and end A will tend to offer the reaction in the opposite direction. Okay, so as far as the reactions at the fixed ends are concerned, the reactions at the fixed ends in case of these machine elements is only because the machine element happens to be fixed at end A and end B. Now the question is, so it means that the positive temperature change is responsible for causing expansion in the material. Okay, and the fixed ends of the material tend to obstruct or tend to stop the material from expansion. Okay, the opposite force or the reaction is applied here, is created here, the reaction force is created here. Now the question is, how much is the value of Ra and how much is the value of this Rb? This is to be calculated. Okay, so let what how can we how we will proceed in this problem. In this problem, first of all, you assume that there is nothing like that of these fixed supports. Just release this material from these fixed supports. So as we remove the fixed supports, so we have a machine element, and the length of the machine element happens to be L. Okay, this is the length of the machine element, that is L. Fine. Now at one end we are having load acting, reaction load, that is Ra, and at another end there is reaction load acting, and that is Rb. Fine. These are the two loads that are acting. Now first of all, let's talk about the temperature change. We know every material has what we call as the coefficient of thermal expansion. Coefficient of thermal expansion, which we define by alpha. Okay, and we define as alpha is the change in length that happens in the machine element, okay, under the influence of a temperature difference. Okay, so there is what we call as the change in length because of the unit temperature difference. Okay, so delta L divided by delta T is what we call as a coefficient of thermal expansion. That is how much change in length occurs in the machine element under the influence of a unit temperature difference. So if you change the temperature by a unit degree Celsius or by a unit or a unit by 1 unit, how much is the change in this? How much is the change in its length? That's what we call as a coefficient of thermal expansion. So it means the change in length that happens under the influence of the temperature difference is coefficient of thermal expansion multiplied by delta T. Okay, so this is change in length, and we know change in length to that of original length is what we call a strain. That is therefore equal to alpha by L into delta T. Okay, and we also know that stress is equal to Young's modulus times the strain. That becomes equal to E alpha delta T divided by L. This is stress. This is the value of the stress. Okay, and we also know, as far as the stress is concerned, stress is equal to force by area. That is Rf by A is equal E alpha delta T divided by L. Therefore, the value of force or the reaction that is created becomes E A alpha by L multiplied by delta T. So this is something very important for us. That is EA alpha by L into delta T is the force that is created in the machine element when the machine element is subjected to a temperature difference, when it's subject to a heat change. So this idea is very important for us in understanding the few questions in the book. Let's talk about few questions in the book and how we can use these concepts in solving them. Let me return back to the books.